Okay, last time we were talking about hardware description language. I just want to emphasize that this is how all digital chips are designed these days. This is the only way to do it. This is the only way to manage the complexity of large-scale digital designs. So if you get a job where you're doing any hardware design, you'll be using this language. There's two of them, as I mentioned last time, System Verilog and VHDL. VHDL is older by a few years, but it's not a very nice language to write code in because it was designed to be very verbose, and you have to do a lot of typing. Function and array, and there's a lot of verbosity in the language, which it was designed that way so it would be self-documenting and easy to read, but it's cumbersome to write. So I used to teach VHDL, but about 5 or 6 years ago we switched to Verilog. Since that time, the book has switched from Verilog to System Verilog, which is the more modern form of Verilog. A little problematic though, because the free simulators that I found online, like Icarus Verilog, don't work well with System Verilog. So when I go through this chapter, I will highlight differences from Verilog to System Verilog. So because it's pretty easy to, once you know one, you can toggle back and forth. So HDL allows you to do simulation and synthesis. Simulation is where you're validating the behavior of your circuit to make sure that the logic works. And synthesis is where you can think of it like compiling. You're taking your HDL and translating it into a form that you would implement. In this case, it would be gates, digital logic gates that are connected with wires. And that's usually called a netlist, that representation. So when you have a traditional high-level language like Java, it's compiled to some executable form. It's kind of the same idea with HDL, except it's compiled down to a schematic of gates and wires that could be either implemented on a programmable logic device like an FPGA, or you could use it to design a chip that you're going to send to a fab and actually have made into an application-specific integrated circuit, an ASIC. Okay. Now the problem with there's two challenges with learning HDL. One is that it uses concurrent semantics because hardware is concurrent. There's no notion of a program counter or a line of code that's currently being executed. So all lines execute at the same time. The way you can think of it is everything's triggered by something. Every output that's set by a line of code is triggered by one of its inputs changing. Does that make sense? So you have to change the way you visualize how these programs are executed, because they're not really programs, they're hardware descriptions. The other challenge is when you're writing Verilog, you have to think about what sort of hardware you expect the circuit to generate. So you have to think in terms of combinational and sequential logic, and I'll talk more about that in this lecture. There's also this notion of a module. VHDL calls it an entity, and Verilog they call it a module, but it's the same thing. It is you could think of it almost like a class in an object-oriented language, but it is a unit of modularity, and it is what you take multiple modules and plug them together to form a larger, more complex design. And then that design itself is a module that could be then used in an even more abstract system. So this creates a design hierarchy. The challenge with that is that when you have a wire that's connected to a module, it will be known as one name potentially when you connect it to that module, but when you go inside that module, like when you're debugging, for instance, simulating, you drill down inside that module and it may be called something else, even though it's the same signal. The reason this is confusing is because you have to think of what the context of all the wires are when you're debugging, when you're designing. But when you synthesize your circuit, the hierarchy gets flattened out. So the whole design hierarchy is only there for the purpose of your design process, but when you convert it to hardware, ultimately the whole design gets collapsed down to one flat sea of gates and wires. You guys with me? So in reality, the whole concept of this design hierarchy is not, there's nothing in the design the hardware that's generated from the synthesis that indicates what the hierarchy was. The hierarchy is only there for design purposes. Now, one of the questions that you'll run into constantly when you do HDL design is, should I design this big module, or should I break it into smaller modules? Well, it's up to you. That's kind of a matter of personal preference. Everyone has their own style. Some people prefer to have fewer modules and make the modules larger. Others have smaller modules and then have more modules. Does that make sense? So kind of the same, some of the principles, same as the principles from software. You know, when you write software, you could have more methods that are smaller. You can have fewer methods that are longer. Okay, behavioral module describes the behavior of a module. Typically, that's going to be a truth table or a finite state machine, right? Because that's or Boolean logic, which is the stuff you guys know all that already. So behavioral HDL is essentially describing the behavior in terms of things that we've already seen in class. Boolean logic, truth tables, finite state machines. Structural HDL is when you're designing a circuit in HDL, meaning that you're not putting any behavior in. You're just saying, I want to take this module and stick that in here, and I want to take another module and put that in here, and I want to connect them with wires. So it's kind of like building a schematic or a block diagram using HDL. Now, some people would say, that's insane. Why would you design it like that? That sort of design process is much better suited to a schematic capture tool, like drawing a picture, like what engineers do. They design something, and they actually design it graphically. Yes, and I actually used to teach. I used to teach this class like that. We had a tool called FPGA Advantage or HDL Designer, which was a schematic capture tool. You'd actually design these things. All the structural HDL anyway, you would design as a schematic, and you hit a button and it would generate the HDL, the actual program for you that would get passed down into the compiler. I stopped doing that though because of a few reasons. One of which was if you got an error in the synthesis or simulation, it would refer back to a line number in the HDL, which you've never seen because you didn't write it. You just designed a schematic and the HDL got generated. And the second reason I stopped doing that is because I started doing more collaborative projects with companies like Convey Computer and Texas Instruments and a few other companies. And I realized that all those guys in industry, they all use HDL. None of them use those schematic capture tools. Those are kind of just for learning. I mean, they're not, in industry, they write HDL in a text editor. There's no graphics, it's all text. So as a result, I just switched to just the raw HDL. You guys with me on that? Okay. Okay. So here's an example of a system Verilog module. This one is almost too simple. In reality, you would not have a module. You could have a module that's one line of code, but usually, if you wanted this behavior, you would just have this line of code inside another module that was more abstract. You guys with me? So because typically, and this is something I don't know if I mentioned last time, but the convention is to have one module per file. So it's a lot like Java where you have one class per file. So this would go into one file called example.sv, system Verilog, right? So if you had a bunch of modules that were really small like this, you'd have a huge amount of files in a large scale design. But this is just this is just kind of a simple example. This thing kind of introduces you to the syntax of system Verilog. It as Hendrik noted, I think last time, it looks a lot like MATLAB in the way that it's set up, the way the syntax, the structure. the first line of the file is usually module, although sometimes there's some other information above this, like the time scale or include files. But in this class, you'll usually see the module up at the top, the module line. The module line starts the module, and it has a name, and then you have the inputs and the outputs of the module. You don't have to have the inputs first and the outputs second. They can be mixed up. The other thing you'll notice is this is a common convention in system Verilog that's used. Notice that you say input logic A, B, C, and then you have output logic Y. It's like, okay, well, A is an input. I got that. Y is an output. But what is B and C? They're not. It's not clear, right? There's no label. There's no declaration for those. Well, the reason for that is because B and C take on the type from whatever the most recently declared type was in the list, right? So A, B, and C are all inputs. Now you could say input logic A, comma, input logic B, comma, input logic C. That's fine too. In fact, some people may prefer doing it that way because it's more clear. In fact, some designers will put each input and each output on its own line. So they'll actually put line breaks after these as well. In fact, I think that does make it easier to read, especially if you have a whole bunch of these. Keep in mind, too, that once the module becomes sufficiently complex and abstract, you could have hundreds of input and output ports on it. I mean, you know, really, because like when you have any type, and this comes up like when Apple comes out with their new chip, you know, it's a system on chip. So they have a bus or a network on chip architecture. And then they have all these modules that are hung on it, that are connected to it. The system on chip or network on chips can have very complex interfaces, you know, that have lots of signals. So, you know, when you're up at that level, it's pretty common to see hundreds of inputs and outputs on these modules. So in that sense, you know, you can see why it would be really hard to read if you went overboard with this shorthand. On the other hand, if you have simple modules, then it's okay. Okay, so then inside here, the only thing we have is an assign statement. This is called a concurrent assignment statement. And this is a circuit. This statement represents a logic circuit. And everything that's on the right-hand side of the assignment is the sensitivity list, meaning that when any of these inputs, A, B, or C, that's referenced on the right-hand side, when any of those changes value, it causes the Y to be updated immediately afterwards. So this is the concept of concurrent semantics, is that you could have 10 of these assigns in here, but there's no ordering to them. It's just the assign will trigger whenever any of its inputs change. You guys with me? Okay. And then you have end module here. So notice too that there's no curly braces here. They use the MATLAB / bash sort of style where you have kind of an explicit end to a basic block as opposed to just using curly braces for all your blocks. So you have module and end module. The other thing I want to point out that I always thought was strange is you put a semicolon after this but not that, which I don't get. Okay, and then if you were to simulate this, generally speaking, you'll look at the simulation results in a waveform view where time is along the horizontal axis here, and all the signals that you want to monitor are listed kind of one per row, one per line, right? And then, you know, in this case, since these are bits, these are binary. 0 or 1 are shown as 0 being low, 1 being high. So this is meant to look like it's an oscilloscope type of view, right? Which is cute, but once you extend, if you were to extend any of these signals to a multi-bit value, then it would change and it would just show you what the value is. You guys with me? Like, so if A could be 4 bits, in which case A might be 1 or 7 or 9, and it'll be shown here usually in binary or hexadecimal right here. And then the only thing you'll see where the transitions are with vertical lines, but it won't just be low or high. You guys with me? So the whole aesthetic of the logic analyzer kind of falls apart once you go to multi-bit signals. And I have a picture of that coming up here too. And then if you synthesize it, it gets converted to a circuit. This circuit, by the way, is one of many circuits that you could generate that implement this behavior. It's up to the synthesizer and how it actually generates the circuit. You know something's going on here, though, because if you look at this, you can see that there should be not A and not B and not C, and I don't even see that anywhere in the hardware. So this circuit that it generated was a minimized form. It's like they ran it through a Carnot map. System Verilog is case sensitive. There's some restrictions on names. You can't have a name that starts with a number. And you might say, well, every language has its own naming rules. Yes, but this is significant because a 2 mux is something that would make sense, right? Like if I want to create a mux and it has 2 inputs, I might call it a 2 mux. I mean, this is something that you would reasonably call something, but yet it's illegal. So you would call this, mux2 or something. You just have to be aware of that. White space is ignored, which is why, remember I mentioned that you could put a line break after each one of these inputs if you wanted it. It wouldn't make any difference. Or you could put the whole module on one line if you wanted to, which would be insane, but you could do that. So white space is ignored. You can put tabs and line breaks however you want in there. And then comments use the Java/C type comments, which is good. And then let's take a look at a structural Verilog example. And this is actually, I think most of you, having learned an object-oriented language right from the beginning, in CS1 or 145, probably are pretty comfortable with this idea, but you just have to think of it in terms of hardware now. You've got an AND gate, you've got an inverter, and then I want to instantiate an AND gate and instantiate an inverter in this more abstract module and then connect them. But the one thing that might be new is the connections are made through internal wires. In this case, I've got something called logic N1. That's an internal wire. And it only exists inside of this NAND. And it's going to be used to connect the output of the AND gate to the input of the inverter. And it does that through its name. So N1 is connected to the output of the AND gate and is also it is the output of the AND gate, and it's the input to this inverter. You guys with me? So inside the AND gate, it's called Y. So if I were to drill down inside this AND gate, I would have something called Y. If I come up the hierarchy into the NAND gate, it's now going to be called N1. But once I synthesize it, that wire is going to be just one wire. It's going to get flattened. Yes?
So why don't you put output logic N1 instead of just logic N1?
The output, in the input and outputs, the only place you can use those is when you're declaring a module in the module line, right? It's only for declaring something as an input or output to a module that you're currently defining in that file, right? This is just logic because it's not. It's just an internal signal. It's an intermediate signal. I don't know. It's like it's an internal wire. I think the book calls them wire. I think the book still refers to them as wires. And by the way, this is something else I should point out. In Verilog, it would be declared as a wire, not as a logic. So if you see wire, that's because it's Verilog. But in System Verilog, they rename this logic. But it's just a 1-bit signal. But it's not, I mentioned last time, when I say 1 bit, by the way, it could be the value of that could be a 0 or a 1. But it can also be an X, meaning undefined. There's a couple other values, or Z, hide impedance. There's a couple other values between just 0, besides just 0 and 1. Now, one of the other things I want to point out, I think the book excised this part from the first edition. I was looking for it today. I couldn't find it. Another thing you'll notice if you look at any kind of legacy Verilog code, notice that when I declare the AND gate, I say AND3. By the way, notice AND3. It's called AND3 because there's 3 inputs. You might call it 3 AND, in which case that wouldn't be a legal name. So that was the reason that they bring up that naming convention thing. So name 3, and then you give it a name called AND gate, or I could call it anything I want. I could call it, I'll just call it, I'm just going to call it foo or something. Yeah, foo. And I use that name because I want to emphasize that aside from simulation, you generally don't ever need to worry about what you name the instantiated modules. You guys with me? So this is, and3 is kind of like your class name, and foo is like your object name, using the terminology from Java. But foo is the name you give it, but generally you're not going to refer to foo anywhere. No, I mean, there are exceptions to that, but this is really just giving it a unique name. Just you want to give it its own name, right, for the purpose of saying that this is an object that I'm putting in here. And then you say A, comma, B, comma, C, comma, N1. And that creates the AND gate. That's like plopping down an AND gate. Now I could create another one if I want. I could say AND3 foo 2. And I could put stuff in there as well. I could put as many of those as I want, right? But this is giving connections to the inputs and outputs to the AND gate. So there's 3 inputs and 1 output. Now looking at this, by the way, and this is one of the things that really annoys me about this, is that if I'm looking at this code, I have no idea which of these are inputs and outputs from this line of code. It's unclear. The only way for me to know that is to find the AND3.sv file and open it and cross-reference it. From this view, I have no idea. And unfortunately, you don't know, right? You guys with me? But it's the same way in any programming language. Like in Java, you don't necessarily know which of your arguments are meant to be inputs and which ones are meant to be outputs from looking at the method call, right? You don't really know that, right? Unless there's comments or something that tell you that, right? But also notice that the connections are being made according to, so I'm going to say A, B, C, and this will be N1. The connections are being made according to their position. A is first, B is second, C is third. And that way they're connected to the first 3 inputs because up here A was first, B was second, and C was third. Now as you start having larger modules with more inputs and outputs, this becomes completely impractical. Because if you have 100 of these things, how are you going to know what's connected to what? You're going to count? Well, this is the 27th one I've listed, and I got to go back to the original Verilog and see what the 27th one in their list is. Not practical. So there's an alternative syntax to this. You can also go like this. Open parenthesis, all right, and then you say dot A, parenthesis A, comma, dot B, parenthesis B, comma, dot C, parenthesis C, dot, what was it called? Y, parenthesis N1. And this is actually more common if you're looking at any legacy code. Instead of connecting the inputs and outputs according to their order, you explicitly connect them by saying dot, and then you give the formal name as listed in the original file, the declared file, the declared module. And then in parentheses, you give it the actual signal name that you want to connect to it. This is much easier to read. And also, the order that you list these in doesn't matter. I could actually go like this. I could say dot y n1, and then I could put my a down here. And it doesn't make any difference because the compiler will know that I want to connect n1 to the output of this AND gate, right? Just because I've got both names there. You guys with me? So to me, this is a vastly better way to do it. This is the older syntax. This is the newer syntax. You can use either one. Personally, I use this positional syntax for small modules, but anything that has 5 or more IOs, I'll use this syntax. Because otherwise, it's too hard to figure out which wire you're connecting to which IO. You guys with me? That makes sense? So this is a better. Now, for some reason, the book doesn't. The book used to have that in the first edition, but they took it out. I don't know why. OK, so here's another example. This one has 2 inputs and 5 outputs, and they're all 4 bits. 4 bits each. So when you simulate this, oh, I don't have this. Okay, that's unfortunate. Well, when you simulate this, because they're 4 bits, it'll actually show you, usually you'll see a hexadecimal value in the simulation results, in the waveform, as opposed to just low and high, little oscilloscope looking thing. There's not much more to say about that one. Now this one, this is a reduction operator. It's kind of neat, but in my experience, I've not used it too much. Every once in a while, it comes in handy, but it's kind of neat. You can say A is 8 bits and Y is 1 bit. And this is a way you can take A and use this reduction operator to say that I want to take all the bits that comprise A and AND them all together individually as if I had a 8 input AND gate, and then assign the value to a single bit Y output. It's equivalent to saying assign Y equals A bit 7 and A bit 6 and A bit 5 and A bit 4 and A bit 3 and A bit 2 and A bit 1 and A bit 0. You guys with me? So this is equivalent to that. That's just a shorthand way to do a reduction. Reduction meaning I've got a bunch of bits and I want to reduce them to 1 bit by way of an AND operation. Everyone with me? It's kind of cool. You could do it with OR and and there's a few other operations. The book mentions that, but it's, if you don't remember that, you can always just use the longhand form. Oh, one thing I want to point out about this, though, is notice that when I want to take out individual bits, A is 8 bits, 7 down to 0. If I want to take out individual bits, use square brackets, right? This is one of the things that's, if you write in MATLAB and in Verilog, this gets confusing, because in MATLAB, you use parentheses to address individual elements in a vector, whereas in Verilog, you use the square brackets, right? But the other difference, too, is that Verilog is generally indices start at 0, right? So if I want 8 bits, I got to go 7:0, giving me bit 7, which is my most significant bit, and 0, my least significant bit. Everyone, that make sense? So use square brackets when you address individual bits or ranges of bits, and also brackets when you declare a signal. Why can't I just say logic 8A? I don't know. I don't know why they don't. They make you do 7:0, which means 7 down to 0. Yes?
Can you put the numbers so 7 and 0 when you get it in reverse order?
No, I used to think that, and I tested that once. It didn't work. It turns out it made no difference whatsoever. I thought it would. I declared something 0 to 7. I noticed that because Quartus, and I don't know if you ever, in 313, when you do the designs and it generates the code, Quartus generates their signals that way. They'll say 0 to 7. And when I read that, I was like, that's pretty cool. I wonder if I can reverse this, reverse the bit ordering. But no, it doesn't work, unfortunately. I don't know why you can do 7 to 0, 0 to 7. I'm sure there's some historical reason for it. I just don't know what it is. Okay, and then last thing about assignment statements, and this is really important because this is very common. You guys you might not know this, but in Java you can do this, what's called a ternary operator. I don't know if you learned this, but once you learn this, by the way, like for Java or C, you might actually use this a lot. But the idea is you have some condition, right, which could be any kind of conditional, A equals B, A less than B, whatever condition. Then you put a question mark after it. And then you put the value, if true, colon, and then the value, if false. And then this whole thing together evaluates to either one of these two, depending on the condition.
What is it called?
It's called a ternary operator.
So it's the same thing. I use it in C++.
Yeah, I don't know if they teach it in 145, 146. They teach this?
No.
Okay,
I
it's
just use it on my own.
yeah, it's a very common thing, but it's just not, for some reason, it's kind of obscure in the introductory programming classes. In Verilog, it's critical though because it's the only way that you can put conditional behavior in an assignment statement. Because you can't put if statements outside of a always block, which I'll get to in a minute. It's also, in Verilog, it's also how you make a mux. So by doing this, by saying assign y equals s, meaning is s 0 or 1, if s is 1, then I want y to be d1, and if it's false, I want it to be d0, which creates the same behavior as a multiplexer, where s is your select input, and then d1 and d0 are your two inputs to the mux, right? So this is also fundamentally, these muxes are how you steer data around in your design. This is how you reuse components for different purposes. Like for example, if you're making a CPU, you're going to have an ALU in there. But you want to be able to use that same ALU for different instructions, which may get their inputs to the ALU from different sources. And in order to implement that behavior to steer the right operands into the ALU, depending on what instruction you're executing, you have to use muxes for that. So this kind of statement shows up a lot in Verilog, and especially if you're doing architecture or microarchitecture, processor design. This sort of thing shows up a lot. Very common, right? So you want to be comfortable with that. Any questions about that? Okay. Okay, here's another example of a full adder. This one has, is this structural or behavioral? It's behavioral because this is all behavioral. We don't have any other modules that we're instantiating inside of here. This is all just assignment statements and Boolean logic. So this is behavioral code. I've got two internal bits called P and G. That stands for propagate and generate. Propagate is A XOR B. The caret is XOR. Generate is A and B. So notice the syntax here. We've got, this is a Boolean and, ampersand, Boolean XOR is a caret, Boolean OR is a bar. You can use parentheses in there. So what's going on here? We've looked at full adders before. They didn't work like this. Well, the reason why they did it this way is there's a style of adder. You guys know ripple carry adders, right? There's a style called a carry look-ahead adder, which is a vastly faster version of an adder, but it requires a lot more logic, so that's the trade-off. But in a carry look-ahead adder, there's this notion of propagate and generate. So in this case, a propagate means that if I have a carry in, I'm going to take that carry in and send it off as a carry out. I'm going to propagate a carry in, a carry. A generate means that I have so many 1 bits coming in this bit that I'm going to generate a carry out regardless of what my carry in was. That makes sense? So that's what this means. But this reduces down to the same old full adder that you guys are familiar with, because if you take in other words, the propagate and the generate become important when you scale up to multiple bits, but if you're looking inside of one full adder, then this is equivalent to the one that you guys have always known. So propagate is here, so the sum is just the XOR essentially of A, B, and C in. And then C out is generate or propagate and carry in. So if we got a propagate and a carry in, we'll pass it through as a carry out. Otherwise, if there's generate is set, then we're just going to generate a carry out no matter what. Now, what is the point of this? The point is that, I don't know. Actually, I don't know because we got multiple assignment statements and multiple internal variables. I guess that's the idea, right? So it's a little bit more complex than the designs we've seen before. This is the circuit that gets generated from this when you synthesize it. At least that's the one the authors got. You may get something different depending on what synthesizer you use and what settings you specify for it. Okay, this slide is kind of in here as a reference. if you're writing in Verilog and you forget order of operations, operator precedence, or if you just forget what the operators are, this is a handy table. This shows all the operators in Verilog. You've got not, which is tilde. I thought there was also a version of not with a bang. There's bang equals, not equals. I wonder if that's missing from here. Well, anyway, but not is, there's tilde, right? I think if you're using Java or C, a tilde is also not, but it's a bitwise not as opposed to a logical not. Multiply, divide, and modulo are star, slash, and percent sign. Add and subtract, plus, minus. Shift, this is also something that shift is in Java and C. You don't use it much in Java and C, but in Verilog it's much more common because in Verilog you're commonly doing bit twiddling, bit swizzling. There's different names for it. Bit twiddling. It means manipulating individual bits. For example, you've got a signal and you want to be able to take part of the bits and shift them this way and merge in other bits. So that's the shift operation. Arithmetic shift is using 3 of the less than, less than, less than, or greater than, greater than, greater than. I used to think, wait a second, hold on. Arithmetic shift means, you guys remember from 212, hopefully they covered in 212. An arithmetic shift is when you shift to the right, and instead of shifting zeros in, you shift in the sign bit, right? So you don't change the sign. So if I have like -5 and I do a right arithmetic shift by 1 bit, I want to divide it by 2, but maintain the sign. So -5 divided by 2 is -2.5, but it's going to round it down to -3, right? You might say, is that round down? Yeah, rounding down, away from, to the right of the number line, it would actually, round down to -3. But you want to use an arithmetic shift if you're doing shifting to divide by a power of 2. You guys with me? Now, how does that apply to a left shift, though? That doesn't make any sense. If you're shifting to left, you wouldn't be shifting anything sign bit into the right-hand side. That doesn't track. But it turns out that the reason why you need an arithmetic left shift is that if your shift amount is negative, then it becomes a right shift, right? So that way, that's why they have both. Comparison, less than equal, greater than equal. This one you have to be careful of. This one can bite you because, you guys are used to, whenever you do comparisons in Java or C, you're comparing 2 values that have been declared as a certain type. Right? So if you compare 2 integers, you're assuming that they're 2's complement signed integers, and you can have unsigned. And so if you compare unsigned integers or signed integers, it actually does a different comparison. You guys with me? Because the bits mean something different. If you have signed numbers, the most significant bit is the signed bit. If you have unsigned numbers, the most significant bit is just 2 to the power of n minus 1 significance. Right? But in Verilog, you don't have int and unsigned int. Everything's just logic. So you can get in trouble depending on how you do this comparison. So don't take that for granted. And obviously there's no built-in, there's no floating point in Verilog, so you can't, you're not doing comparison that way. So be careful with that. There's ways to explicitly define how you want to do the comparison, but it's a little beyond the scope of this course. There's equal and not equal is double equal sign, so be aware of that. Double equal, just like in C and Java, and then pound equal or bang equal is not equal, and then you've got your logical operations, which I mentioned earlier. Notice that you've got nor, which is tilde bar. That's kind of weird. And then there's the ternary operator, which I mentioned. And the order of operations is highest to lowest. If you have any doubt, you can refer to this table, or you can just use parentheses just to be safe. Right? Parentheses allow you to explicitly define your order of operations. Okay, this is something else that is very common in Verilog. So whenever you specify a constant, like a number, How do you want to write it down? You want to write it down as a base 10 number or a base 16 hex number or an octal number or a binary number? And also, if you specify a constant, like in C or Java, everything has kind of a, basically everything's 32 bits or 64 bits, depending on how you declared it. But in Verilog, you very commonly deal with signals that have some weird number of bits, 5 bits, 3 bits, 9 bits. So you have to be careful that whenever you specify a constant, you also define how many bits that constant is supposed to comprise, right? So there's two parts to this. One is, what's the base? And the second is, how many bits? So the number of bits comes first. So if I type 3 apostrophe B 1, that's a 1. But this is going to be treated like a 3-bit signal. So whenever because I only showed one, I only gave 1 bit, but I said it was supposed to be 3 bits. So that implies that this is there's 2 leading zeros, 0, 0, 1, right? Everyone with me? On the other hand, if I say, let's say I say 5 apostrophe H, which stands for hex, 1A. What does that mean? Well, that's 5 bits in hex. Would you in 212? You did well. A1 is 0001, and A is 1010. Oh, but we got a problem. That's 8 bits.
So that means you have to move it over 3, right?
No, you just wouldn't
Or you just take off. Oh, you just
take off the leading bits in that case. Yeah. So this is 11010. Is that, right? Now you might say, wait a second, I thought every hex digit's got to be 4 bits. No, not necessarily. If you say in Verilog 5 apostrophe H1A, that means that this first leading hex digit can only be a 0 or 1, because if you made it 2, this would require 6 bits, and it would be invalid, right? So there's a bunch of examples of that here. You can also use decimal, like you can say 4 apostrophe D 5. So that would be decimal 5, or let's say 10 is a better example. 10. So you could do that, and so that would be equivalent to a binary value of 1010 or a hex value of A, right? If you don't specify a size, the synthesizer will assume it's 32 bits. But then if you try to assign that to something that's not 32 bits, if it requires, if you have a value that requires more bits than the signal you're assigning to, you'll get an error. But if it doesn't, you'll just get a warning. Now you might say, who cares about warnings? For those of half of you or so that have taken 313, you guys know that when you run a synthesis tool, you very commonly can get hundreds, if not thousands, of lines of notices, warnings, critical warnings, right? It just goes on and on and on. It's like information overload. So you should try, my advice to you is when you write in Verilog, try to not write code that generates any warnings, because otherwise you'll end up with tons and tons of warnings, and you may get a warning in there that's actually important, and you may miss it because there's like an avalanche of warnings from just writing code that's careless, right, where you don't specify the sizes. You guys with me? All right. Okay. I get. Oh, by the way, what I'm saying, by the way, is it's not. What I'm trying to say by that is, it won't give you an error if you don't give it a size designator. So if you just say apostrophe H10, that'll work, but it's going to assume that's a 32-bit signal. And likewise, if you just say 42 with no base, it's going to assume it's decimal, right? Yeah, like decimal is the default base. But not a good idea. It's better to always give the bits in the base. Okay, here's more bit manipulation, bit swizzling stuff. This is kind of cool. you could take a logic, a wire logic signal, whatever, a named variable, and you can slice out bits out of it. So let's say A might be, say, a 4-bit signal. This would take bits 2 down to 1 out of it. So this would take those 2 bits out of A. So that's pretty neat. I don't know of any other language that can do that can actually take individual bits out of a variable. Also, these curly braces allow you to combine multiple subexpressions into one binary value. So in this case, I want to take y, I want to assign y to these 2 bits of A, and then this bit of A and these 6-bit constant value. Over here, this notation is a replication operator. So this takes the least significant bit of B, bit 0 of B, and copies it 3 times. So what you end up with is y is 2 bits, plus this is going to add 3 bits to it. So that's 5. There's 6, one more. And then there's 6. So this ends up becoming a 12-bit. This expression is equivalent to 12 bits. It comprises of 12 bits. And it's formed of all these pieces. Now, keep in mind, though, that this 12-bit signal is going to have an ordering where bit 0 is going to be a 0, is going to be this guy. Why? Because it's on the right. Bit 0 is on the right. Bit 11, which is the most significant, will be the leftmost one, which is actually going to be bit 2 of A. You guys see that? So there's an ordering here that defines the way that each one of these constituent bits lines up with the indices in Y. Everyone follow that? Yes?
What do you mean when you say like it takes out the bits, the amount of bits from A?
Oh yeah. So let's say A. Let me give you an example. So A is I don't know how big A is. I'm just going to assume it's 4 bits. So let's say I declared A like this. I said logic 3:0. Is it lowercase? Lowercase A. So if I declared A like that, and then let's say I assigned A. Assign A equals 4'B0110. Right? Then I take A and I do what they did there is just 2:1. Right? What is that going to be? Well, A is 0110. So bits 2 and 1, that's bit 0, that's bit 1, that's bit 2, and that's bit 3. So bits 2 down to 1 is going to be that middle 2 bits out of the 4, which is 1, 1. Make sense? Can you read that from there? So that would be equivalent to 1, 1, 2, B 1, 1.
So it takes out the 2 middle ones.
Yeah, and so and obviously those could change. Those could change at any moment. And if they do, that will cause this guy to trigger, right? Because calculating Y depends on A, and so or those 2 bits of A. So once you have that in your code and your design has been synthesized or it's simulating, any change of these bits will trigger this line of code and update Y, right? In this case,
New value of A.
yeah, if there's a new value of A, that'll trigger that thing, yeah, and then it'll update Y accordingly. So what is A here? What is A bits 2 down to 0, 2 down to 1? That's the 2 most significant bits of Y. So if A were to change, Y would be updated right away to reflect that change.
And then the second one, B takes the first bit and times it by 3.
Right, yeah, it doesn't multiply it, it replicates it. So if B, let's say B was 0, 1, 1, 0 as well, that's going to take bit 0 of B, which is 0, and it's going to make it 0, 0, 0, right? So it doesn't multiply it, it copies it, it replicates it 3 times. Now you can also put underscores in constants, which is kind of convenient when you're trying to split a binary value up into into fields as you would for, like, say, floating point or instructions and that kind of stuff. So you could say 10 apostrophe B, and then you could say 0, 1 underscore 0, 0, 0 underscore 1, 1, 1, 1, 1. And that would be valid. It just, the underscores get ignored. But they're useful if you're reading this code and you want to be able to, for some reason, call out the different ranges of bits of a value. So you see underscores show up a lot. That's pretty common. But that, like I said, that just gets ignored for when you compile the code. Okay, here's another example. There's nothing really new here. This is just another example. So this is a 2-input 8-bit mux, but I want to build it from pieces which are 2-input 4-bit muxes. So in order to do that, I create 2 of these smaller muxes and map in. I use one of them for the lower 4 bits, the least significant 4 bits of A, B, and Y. And I use the other mux for the most significant 4 bits of A, B, and Y. But notice that the select is the same for both, right? So this select bit is just 1 bit because it's a 2-input mux. But it's used for both of these guys. You can see that here. You see the select comes in this guy, and it fans out and goes into the other one. So the select is common. But the inputs are 8 bits, so I steer 4 of the bits into one mux and 4 of the bits in the other mux. And likewise, the output of the mux is also 8 bits, but it gets 4 of the least significant bits come from this submux, and the 4 most significant bits come from this submux. Now you have to be careful when you do this, though, because I think I mentioned last lecture that each of these things are driving, Y, each of the bits of Y can only be set by one module, right? So normally, if you had Y connected to both of these guys, you would be double driving it. You would overdrive Y. But it's okay here, though, because I explicitly only I'm setting the lower 4 bits of Y here and the upper 4 bits of Y with this one, right? So it's the same signal, but none of the individual bits are being double driven. Does it make sense? Right? So this is a little, like it could be dangerous. To be careful with that. And then this is something that's not as common, and I'm giving you a little I'm editorializing a little bit just to give you, in my experience, you don't do a lot of this. Sometimes this shows up whenever you have like a common bus that you want to have. If you do want to have 2 modules that drive one signal, but only have one do it at a time, you can use this tri-state, which is when you assign a z. In this case, I've got A is going to get assigned to Y when enable is 1. Otherwise, it's going to get assigned to Z. This notation is strange. Look, 4 apostrophe BZ. 4 bits of Z. 4 Z's. Right? Meaning that I want to physically disconnect Y from this guy when enable is 0. So we looked at this in chapter 2. This is a buffer, right? And this is how you would describe it. Now, this is kind of weird, though, because I told you that if you do 4 apostrophe, I just said that if you do 4 apostrophe B1, this is going to have zeros padding that, right? But yet, if I say 4 apostrophe BZ, would that not be 0, 0, 0 Z? No, apparently Z is, see, I wouldn't trust it. I wouldn't trust this. This to me is, you're assuming that I would have put 4 apostrophe B Z Z Z Z just to make it clear that I want 4 Z's. Because if you put 4 apostrophe B1, it's not going to put 4 ones. It's going to put 3 zeros and a 1. But for apostrophe BZ, Z is special in this case. It will, in this case, it's going to put 4 Z's in here, right? But, or you could just play it safe and just explicitly type out 4 Z's. You guys with me? Yes.
So if the output, like y, was 4 bits and the input a was 2 bits, that wouldn't work? Or would that work?
No, that wouldn't work. That's a good question. Yeah, if A was 2 bits or if Y was 2 bits and A was 4 bits, or vice versa, yeah, it wouldn't. You would get a warning and maybe an error or maybe a warning, but either way, it wouldn't be good code because it would be unclear. Like if Y were 4, if A was too small, right, then what would assign the other bits of Y? It might create a latch. It would be kind of unpredictable what the synthesizer would do in that case, right? On the other hand, if A was too large for Y, then like say A was 4 bits and Y was 2, would it just put the least significant 2 bits of A into Y and ignore the, unclear. You don't want to write code like that. If you're going to do an assignment, you got to make sure that you got equal number of bits that you're assigning.
So it has to be a minimum of 3 bits?
No, A has got to be 4 bits and Y is 4 bits, so A has to be 4 bits. Whatever your output is, it has to match the input here, right? Unless, you could do something like this. Say A was, say I declared A like logic 4:0 A, and I had logic 1:0 Y, right? I could assign Y equals A, but because Y is 2 bits and A is 4, I should do something like this, right? I should say A bits 1 down to 0 assigned to Y, right? That's what you should do, right? Because if you don't put that, then you're saying, well, A is 4 bits, Y is 2 bits. You're leaving it up to the synthesizer to decide how to deal with that. And I know from experience that when you do that, it often screws up. But you won't get an error. See, that's the other thing is you're like, wait a second. When you write code in C or Java, the slightest problem with your code will cause it not to compile, right? The slightest problem. You forget to declare something. You do the smallest problem and it won't compile. But in Verilog is shockingly forgiving for being a very low-level language, right? You can get away with, like, depending on what software you're using to simulate or synthesize, you can get away with not even declaring a variable. And it'll be like, oh, you didn't declare it, so I'll just assume it's declared. Right? It is really shocking. But the problem is when you do that, it often leads to incorrect designs. So you have to be careful. You should try to be disciplined when you write your code. Yes?
What's a good simulator?
What, sorry?
What's a good simulator?
That's a good question. In this class, we usually use Model Sim. Model Sim is from a company called Mentor Graphics, and it is a very powerful simulator. There's another version of it called QuestaSim too that's even more powerful. I don't even know exactly what. QuestaSim has more modeling features in it than Model Sim. Synopsys has another simulator called VCS that's very powerful. Both of them cost a fortune. They're both commercial tools. That's the problem with them. For a free one, there's one called Verilog, Icarus Verilog, and there's another one called Verilator. However, I just found out today, I didn't know this until just about an hour ago, that Icarus Verilog doesn't understand system Verilog. It only understands pure Verilog, meaning that none of the examples in this book will work in Icarus Verilog, which really stinks. Verilator, I don't know yet. I was about to check that and I ran out of time. But I'll get back to you. That's a good question. I think Verilator might be a good option.
Verilog is from that same company you mentioned that it does accepted system Verilog.
No, Verilog is an open source project. Just some dude, some hobbyist wrote it and put it out there.
It's fine. I'm going to download it from the port, from the Mac port.
Oh, actually, no. I take that back. I think Icarus was originally developed by a company that They just decided to give it away for free or whatever. But
A couple open source, but none of it was explored.
yeah. Now the question is, synthesis tools. How to convert that to hardware? I have never found an open source synthesis tool. If you find one, let me know. But that is a bridge too far for open source. Converting, actually doing this to this. Doing exactly what's on the slide. Taking this and generating that. There's no open source as far as I know that can do it. There's a website called EDA Playground that provides a cloud-based version of this to do simulation and synthesis. But if you go there, it turns out that under the hood, they're just using the commercial tools. But you can do it through their website for free. So it's kind of cool. I haven't played around with it too much. But yeah, in general, this stuff is pretty arcane, unfortunately. OK, so moving forward here. OK, here's another kind of a neat thing you can do with Verilog. You can put delays in. So you can put a hash symbol, £, with a number puts a delay on an assignment statement. First of all, first question you probably are wondering is, what are the units? Right? What are the units? The units are whatever the time spec is, time scale, which could be defined in either your simulator or you can put it at the beginning of your Verilog code with a little tilde time scale command. Usually you don't care about the units though, because normally, usually, almost always, when you run simulation of Verilog, you're only testing functionality. You're only doing a behavioral simulation. So you're not trying to, you don't care about delays. You don't care about logic delays and propagation delays, because you don't care about that until you move into the hardware and you synthesize this and try to place and route it into a technology. Usually you only care about the behavior. And with regards to behavior, all of the logic happens in basically an infinitesimal amount of time, epsilon time, right? In other words, if something over here changes on the right-hand side, the left-hand side is updated immediately. I mean, not 0, but epsilon. Any amount of time beyond 0 will cause the update to happen. You guys with me? Which is, in reality, is unrealistic because real hardware doesn't work that way. There's a propagation delay, as we learned. But we don't care about propagation delay when we do this kind of simulation, right? However, in some rare cases, you can go and you can synthesize your code, put it into a technology, and then back annotate the Verilog with delays, which allows you to simulate delays. And when you do that, the way it's done is it uses these little hash marks, right? The problem is that this Verilog now is non-synthesizable. You cannot synthesize any Verilog code that has any delay information in it because it's non-synthesizable. But if you synthesize Verilog and back annotate the delays in, that allows you to model code that you've already put on a specified technology. Does that make sense? It's kind of esoteric, and this is not very common. But if you look at what's happening is that this is saying assign N1 after 2 units of delay. So if you look at the timing diagram here, which the authors were zoomed in on this really tight. So you can see that CB, A, I have to figure this out. A changes at the beginning, and then CB, a CB is assigned as part of this group of 3 signals that are assigned. Notice in this case you got the parentheses, the curly braces, but in this case they're used on the left-hand side of an assignment, which this is actually the first time I've shown that. Right? So I'm assigning all 3 of these as one signal, one concatenated signal. So CB gets assigned, but after a unit. So notice that there's a one time unit, whatever the time unit is, could be nanoseconds or picoseconds, but it gets changed. CB is undefined, that's what this gray line means, and then it gets assigned after 1. You guys with me?
You're setting A, B, and C. You're setting A, B, B.
Those get set right off the get-go, yeah. And that's not shown because those are inputs, so we don't see that happening. but according, we don't see that happening in this design, but they're inputs here. So if you look at this design and you look at the timing diagram, you can see that A, B, and C are right off the time 0, they get set, right? And because those will activate, A, B, or C activates the assignment of these 3 signals, CB being one of them, or actually AB, BB, and CB, they're all 3 shown here, they have a delay of one unit. Make sense? Okay. All right. Well, that's I think that's all the time I've got. I will see you on Wednesday.